Hi everyone, welcome back. This is Earth and Space Science 101. This is our second lecture. We're going to talk about geologic structures today. It's going to be a direct segue from everything we learned in lecture 1. So make sure and watch these in order. You definitely need all the information we covered in lecture 1. So what we're going to be talking about today are essentially going to be the faults and the folds, basically these are just names for geologic structures that are going to be the result of plate tectonics, and in particular the stress that builds up as a result of plate tectonics. One very, very important thing to keep in mind for everything that we talk about today is that these are almost exclusively smaller scale features than the things that we were talking about in Lecture 1, where in Lecture 1 we might have been talking about something like the Mid-Atlantic Ridge that spans from the North Pole all the way down to the South Pole. We might be talking about a single fault along one tiny part of that overall mid-ocean ridge today. So these are definitely going to be smaller in scale, but when you look at these in general and you look at these things overall, you can see that they are the direct result of all of the stresses that we've been talking about so far. So, mainly these are going to be folds and faults. But before we get into the geologic structures themselves, I want to kind of set the stage for you. We're going to talk about various types of geologic stresses, where those stresses are going to be common, and then we'll be able to go from there. We'll cover a little bit of background information first. Now, this image on the very first slide that I wanted to show you, the image that you can see right now, is going to be of both a fault and a fold. Over on the left-hand side of the image, you can see that these layers of rock are actually not flat. They are folded up almost like, practically like an accordion. They have these big curves. That's going to be a geologic structure called a fold. Dividing everything that's happening in the left side of the image from the right side of the image is a large fault, and that is a break in the rocks that's lowering everything on the right-hand side of the image from everything on the left-hand side of the image. So that's why I like this particular image. It's like a lot of different geologic structures all in one glimpse. And you can see all of these people for scale all surrounding this image. What you're seeing is a road cut. So this is a place, obviously we don't have anything very similar to this in Louisiana, not having a large amount of topography, but this is a place where they've actually had to blast through layers of rock to build a road and to be able to make the road have as low of an incline as possible. So these are favorite places for geology students to go and to learn about some of these geologic features and to be able to study these features. So the root cause of all of these geologic structures, the cause and the cause and effect relationship here is going to be stress. Now, in geology, we use this term a lot different than you do in your everyday life, but there's still sort of a cause and effect relationship between the two. Your definition of stress might be having way too many exams all in one day. And the result of that stress is that you might not study very well for any of them and not do very well on those exams. So there's a cause and effect relationship there. In geology, a stress has a much more sort of narrow overall definition. A stress is just a force per unit area. So it's a push, a pull, or a slide, something that is going to be manipulating some layer of rock, some part of the Earth itself, whether it's near the Earth's surface or deeper into the crust. Stress is going to result in strain, and there are different types of strain as well. We'll talk about that in just a minute. But first I want to talk about the different types of geologic stresses that there are. These basic stresses include what we call a compressional stress. That's going to be when you push on material. When you pull on material, that's going to be called a tensional stress, like tension on a rope. And then the third overall type of stress is going to be a sliding stress. Essentially, when I have my hands sliding past one another, that's a shear stress, that's a sliding stress. So there are images that show the result on the same thing that I'm going to be using, which is silly putty, but we're going to go into these overall 3 types of stresses. Now, what we're going to do first is expose this silly putty, and you can kind of think of this silly putty as the way that rock is going to behave deeper down in the crust, where it's really hot and the pressure is really high. Rocks don't really behave the same way that they would on the Earth's surface, where they would behave brittly. Things are more likely to behave in a slightly more ductile way. So whenever you push or pull on this material, it might not necessarily break, or it may eventually break, but it might initially act in a little bit more of a plastic way. So if I take this silly putty and I compress it first, I'm going to squeeze it, and the result is going to be that it just gets shorter. So if I had some structure to it already, like if it was a rock laid out in a flat layer like this, and then I compressed it, I might end up folding that originally flat layer. One of the basic assumptions in all of geology is that sedimentary rocks are going to be originally deposited in flat layers. So that when later on you see these as being folded or faulted, we know that those have been exposed to some type of stress, and that some geologic structure is going to result in the appearance of what you're seeing. Now, first thing we did was a compressive stress, so we made something shorter. The next thing we're going to do, I'm going to ball this up again, is we're going to take this silly putty and we're going to expose it to a tensional stress. And just like you would expect, when we pull on it, it's going to make it longer. Eventually, if I pull on it enough, or if I pull on it really suddenly, it's going to break. So we have eventually brittle deformation from this material that was originally acting in a ductile way. The last thing that doesn't translate very well to silly putty is a shear stress. And again, that's when you're just basically taking this material and pushing in opposite directions. So the result might not be that you overall lengthen it or shorten the material. You're basically going to warp the material. You see this more in the way that certain minerals are going to look after being exposed to a shear stress, particularly when we're dealing with types of rocks called metamorphic rocks. So I'll get into a little bit more of that later. So your stress is going to be the cause, right? Very similar to the cause of a broken bone might be if I fell on my arm. If I fall down on my arm, that's going to be the cause of the break in my arm. The effect, the break itself, is going to be the strain. In geology, the strain is going to be the result of stress. It's a cause and effect relationship. So in strain, this could be any kind of change that the rock undergoes, whether it's lengthened or shortened, or the minerals are going to be in a different shape than they used to be, any result from the accumulated stress. Now, the way that the rock is going to behave when exposed to stress is going to be different depending on the type of material involved, what type of rock you're dealing with, and most importantly, whether you're dealing with rocks that are closer to the Earth's surface under lower temperatures and pressures, or at greater depths away from the Earth's surface under higher temperatures and pressures. So there's no exact depth where this change is going to occur. I won't pretend that there is, because it is going to be also dependent on the type of rock involved. But let's just suffice to say that the deeper parts of the crust, the upper part of the mantle, those are going to be rocks that behave more like the silly putty did. When exposed to some kind of stress, they would be more likely to bend, less likely to break, at least for a little while. Closer to the surface, rocks are going to basically behave the way that you would expect them to behave. When subjected to a stress, they are more likely to break instead of bend. So, those rocks closer to the Earth's surface experience brittle deformation. That's the breaking, right? That's typically expressed as faults. Rocks exposed to higher temperatures and pressures deeper down in the crust, those are going to deform ductily. You're going to have ductile deformation. So that's essentially, again, where rocks behave more like silly putty. Now, as we saw earlier, when I pulled on that silly putty, if I pull it fast enough, and if I pull it away, if I expose it to a tensional stress, eventually it's going to break. And that's going to be throughout the crust. So it's possible to have faults in the lower part of the crust. It's essentially just very difficult to have things like folds very close to the Earth's surface. So when we see things like folds, when we see evidence of ductile deformation exposed on the surface of the Earth, we can then interpret that that must have happened a very, very long time ago, in some cases millions of years ago, and a substantial amount of erosion of all of these overlying layers of rock has already happened. So we're just seeing essentially the feet of what used to be a whole, maybe something like an entire mountain. We're just seeing just the very, very bottom part of all of that action where all that ductile deformation was taking place. Sometimes this could be miles below where the brittle deformation is actually taking place. So, the other thing that we need to cover first, before I get into the actual geologic structures themselves, is how we're going to refer to these things in space, how we're going to talk about the layer above the fault and layer below the fault, how we're going to talk about the orientation of something like a fold. Now, all of this probably doesn't sound that difficult to do until you're actually standing out in the field, looking at a layer of rock and saying, okay, if I'm going to try to describe this experience, if I'm going to take notes on this, if I'm going to write up a paper on this, how would I then describe how these rocks are actually oriented? How would I begin to do that? This is particularly important for us because the names of the different types of faults are going to originate from these names that we give to the orientation of some feature. So the orientational terms that we use in geology are strike and dip. Now, if you just wanted a flat definition for these, it's going to not be enough to really tell you what's going on. It's not going to give you a visual, but just a definition. The strike of a feature would just be the orientation of that feature at the surface. The dip of the feature is the angle that it makes with the surface of the Earth. But it makes a lot more sense when you actually see this in action, when you can actually see it in a visual. The image that I'm showing you right now is of several layered rocks, and it's very important to remember these rocks were all originally laid flat. They were all originally horizontal, flat on the Earth's surface. Some event happened later on, like mountain building, that took these originally flat layers and then tilted them on end, almost to make them completely vertical. You need a lot of power to be able to do that, but plate tectonics provides that power to reshape and to relocate these layers of rock. So they were flat. That would mean that their overall dip originally was 0 degrees. Now they're almost completely upended. So let's go ahead and call that maybe like a 70-degree dip. 90 degree would be perfectly vertical. Again, 0 would be perfectly flat. So the angle that these features make with the surface, that has a dip or an angle of 70 degrees. Now, the strike is impossible to tell from just a sheer image of this because we don't know the overall orientation of this picture. You don't know where the picture taker was in space when he took this picture. So we have sort of incomplete information on this individual picture here. But let's say that there was a road running right next to these layers of rock, and that road was oriented perfectly north-south. So you could be driving north along this road and drive right by all these layers of rock. That means that the rocks themselves would have a strike. That line that the rocks make with the surface of the Earth, that strike line, would be a strike of roughly north-south, or 0 degrees on a compass. So the strike is always going to be perpendicular to the dip. So it almost makes more sense to talk about the dip first, sort of the up-down orientation, if you will, the angle that these features are going to make with the surface. It almost helps to think about that first and then think about where the strike is. Another thing that typically sort of happens that's helpful with this idea is to look at a picture like this where these layers of rock are tilted, but in this little cartoon here, you have them up against water. So some of these layers of rock are actually submerged underwater. The angle is then the angle of that topmost layer of rock with the surface of the water, and that angle in the cartoon is a 30-degree angle. The line of strike is the line where the water comes in contact with the layer of rock, and that might be north-south, or east-west, or northeast to southwest. There's no reason why these things have to run in perfectly cardinal directions. I'm just using that to kind of make it a little bit easier to conceptualize. Now, the reason why strike and dip are very important is because we're going to talk about faults that have a strike-slip orientation, or that means that there's going to be movement along the strike of the fault, and then faults that have a dip-slip motion. So that means that the motion of the fault is going to be along the dip of the fault. It becomes really, really difficult. It takes a lot of time, and I would stress that you need to spend a little bit of time with this, maybe even sort of draw up some cartoons to make it make as much sense to you. I'll admit to a definite weakness on my part. Structural geology has always been one of the hardest parts of geology for me, because I'm not one of these people that has a really easy time picturing things in a three-dimensional space. People like artists and architects, and engineers. These kind of people have a really, really easy time picturing things in three dimensions, and this concept of strike and dip, that usually isn't any kind of a problem for them. If it is a problem, just spend a little bit more time with it. Work on that particular part of the problem. So the strike and dip, like I said, it's going to be very important to covering different types of faults. It's also important for the subject of folds, but we're not going to really use these names in describing the different types of folds. So put that on the back burner for just a minute while we talk about folds. Now, remember, when you're dealing with rocks deep, deep below the surface that are under high temperatures and high pressures, they are not going to act like rocks in your driveway. They're not going to respond to stress simply by breaking in half. Typically what's going to happen, especially with compressive stresses, is that these rocks are going to bend. So again, just to make sure it's completely understood here, if you have some flat layer of rock like this silly putty, and I squeeze that silly putty, the response is going to be to bend. So you may have rocks, and all of these were originally laid out flat with respect to the Earth's surface, that might end up in crazy, crazy orientation folds. They might be overturned. They might be anticlines and synclines. There's all kinds of terminology, especially covered in your textbook, used to describe these different types of folds. What I think is the really important thing to take away from all of this is that folds are going to be the response of ductile deformation. They're going to occur very, very deep within the crust. And they are always going to be the result of compressional stress. Think about it. If you take some flat layer of rock and you pull on it, at no point can you make it folded. But it only takes a very slight amount of compressional stress to fold the rock. So you have to squeeze, you have to push. Compressional stress is going to be more common in things like mountain building at convergent plate boundaries. So that's going to be pretty much where you typically are going to form folds. They're going to be found at the base of mountains as they're forming. Later on, once those mountains have eroded down, then they might actually be exposed to the Earth's surface, but know originally that they were formed at the base of those mountains, far below the surface of the Earth. So ductile deformation is going to be responsible for the folds, ductile deformation and compressional stresses. And we have different types of folds like anticlines, synclines. Essentially, these are just the orientation of that fold in space. So if you have an anticline, you might have this silly putty squeezed together in such a way that the fold is pointing upwards. An anticline makes an A. That's another easy way to think about it. You basically have this fold pointed upwards towards the sky. If you have the opposite scenario, where that fold is pointed generally downwards, even if there's some angle to that fold overall, if it's generally pointed downwards, if it makes a bowl, it's a syncline. So in the cartoon that accompanies some of this information, you'll see that you have anticlines and synclines all in the same feature. You have fold upon fold here. So you've got anticlines and synclines all next to each other. The synclines are just the downwards pointed folds. The anticlines are just the upwards pointed folds. So all of this is going to really be the result of only one type of stress, and that stress exposed to the deeper parts of the crust. So folds aren't really all that common overall. The much, much more common geologic structures are going to be different types of fractures, and these include faults. A fracture is just going to be basically any case where you've had some layer of rock and it is broken. It doesn't mean that there's necessarily going to be displacement along that break, just that the rock is broken. So a type of fracture where you don't have any displacement, where the rock is basically just broken, but there's no offset, is going to be a type of geologic structure called a joint. So the analogy would be to compare it to something like, let's say I had a break in my arm, and it would be what a doctor would refer to as something like a hairline fracture. A hairline fracture would be similar to a joint in a rock. There's a break, but there's no offset of the bone. A really, really nasty break in a bone, where the bone is actually offset, that would be analogous in geology to a fault. So joints, like columnar jointing, seen in the images here, that is no offset, no displacement. A fault does have displacement. Now, the faults are almost always going to have most, not all, but most of their displacement either up, down with respect to the Earth's surface, so that along the displacement along the fault, you might have the layers offset in such a way to where one layer is above the other or one layer is below the other, but that displacement has occurred along the dip of the fault, or sort of more of an up-down motion, or side to side, and we call those strike slip faults. So to help us sort of make sense of all of this and to kind of give us a little bit of an idea of how we're going to refer to these different layers of rock, it's very important, first off, to picture these as three-dimensional features. You're also picturing a pretty large area. You know, so you might be looking at like a square mile up in the Front Range of the Rockies, where you'll have some amount of area, a whole big section of land that's been dropped down because of the fault, and then some part that's been raised up because of the fault. So take a look at this next image here, and you'll get a little bit of a better idea of how these faults work. In this image, the fault is really running right along the beginning of the mountains. So that line right along where the mountains meet the landscape in the picture, where you have all the green grass and the meadow, that's basically going to be the strike of the fault. And in this particular type of fault, you don't have any displacement, or you have very little displacement along the strike itself. Almost all the displacement is along the dip of the fault, along that angle that it's making, right? So you can see this because these layers have been cut away thoughtfully in this little cartoon image so that you can actually see the subsurface. You have this sort of polka dotted kind of tan layer in the image, kind of a cream colored image. And then below it, you have a different layer of rock that's more of a purple or reddish kind of color. And you can see how that layer has been offset. The contact between the sand above, which is that kind of khaki colored material, and the shale below, which is that dashed pattern with the purple, you can see that the contact between those has been offset by the fault. The fault is that line of yellow right there. And along that line, in this particular scenario, you also have ore minerals. So you might have gold, silver, palladium, all of these different minerals that precipitate out along faults because water's coming up into this fault. And if it particularly it's hot water, it's laced with these particular minerals that then precipitate out along the fault itself. So, okay, now the stage is set. We can kind of begin to understand some of this terminology that we're going to need to describe what's happening along this particular type of fault. Geologists use the terms hanging wall and footwall to describe what's going on along the fault itself. And the origin of these terms comes from this idea that you might have a person in a mine along these faults. And mines are typically drilled and excavated along these faults themselves, again, because you have precious metals and precious minerals that might be found along this fault. So let's say right along the fault itself, you have a mine, you have a person standing in the mine, and there might be a hook on the ceiling where they might hang their hammer or hang a lantern. Everything that's part of that block of material, everything that's above the plane of the fault, is referred to as the hanging wall. So that's essentially everything that makes up the meadow on the surface to miles and miles below the surface in this image. That entire area is the hanging wall block. Everything where the person's feet might be standing and below, so everything below the plane of the fault, is referred to as the footwall block. So I would invite you, when you're trying to kind of figure this out at home, to maybe draw a little image of a fault and draw that line that indicates where the fault is and put a little stick figure of a person on the fault. Wherever his head is, that's the hanging wall. Wherever his feet are in the image, that's where the footwall block would be. And now that we have a way of describing these that's not going to be unique to just one situation, but applicable to all situations, we could begin to understand the different types of faults. Now, in this image, this very first image that I just had finished going over with the hanging wall and the footwall, you have what's called a normal fault. I'll describe in more detail what that means in just a second here, but it's because the hanging wall is dropping down relative to the footwall. It's a dip-slip fault. It's one of two different types of dip-slip faults, and it's one where the hanging wall is going to drop down relative to the footwall. In the next image, we have the opposite sense of motion. This is more like it's not a cartoon, it's a real image of an outcrop where a fault has taken place. And as is mainly the case in real geology, it's a lot harder to discern the different layers of lithology here. It's a lot more difficult to kind of figure out what's going on in the image. But you may be able to see in the image this light gray layer that cuts right through, cuts up to the fault, and then it picks up again a little bit lower down in the image, and then cuts over to the right. So you can see where this layer has been offset, one, so that means it's definitely a fault and not a fracture. Two, you can see that the offset along the fault is happening along the dip of the fault and not the strike, because all of this is happening at an angle. It's all happening in profile view. So we can tell that it's a dip-slip fault too. And then finally, we can tell that this is a particular type of dip-slip fault called a reverse fault. It's the reverse of quote-unquote normal. Normal faults have the hanging wall moving down relative to the footwall. In the case of a reverse fault, the hanging wall moves up relative to the footwall. So, let's go through these again. So, just so you have the definitions to go with all of these and a nice little cartoon image to accompany each. In dip-slip faults, and that's any case where the displacement along the fault is along the dip of the fault or the angle that the fault is making with the surface. In any dip-slip fault, it's the hanging wall moving up or down relative to the footwall. In a reverse fault, like the image on the top of this slide, you can see that it's the hanging wall moving up relative to the footwall. And these are seldom perfectly vertical faults. They may be high angle In some cases, sometimes they might be low angle, but you can always see that the overall general motion is going to be that that hanging wall is moving up and maybe to the side a little bit. So up relative to the footwall. These types of faults, anything that falls in the broad category of a reverse fault, is going to accommodate compressional stress. So if you have some stress, like the stress that accompanies mountain buildings, and it's pushing in on either side, then that's going to take the hanging wall block and push it up relative to the footwall block. Particularly in mountain building, it's typical for these faults to have very, very low angles. So a low angle reverse fault is just called a thrust fault because one block of material might actually even be thrust on top of another. That would happen if you had a really low angle for the fault itself. So not to throw too much terminology at you, but just remember reverse faults are the overall category. It's one of their 3 overall types of faults. And a thrust fault is going to be a type of reverse fault where you have a low angle. For normal faulting, the type of stress is going to be different, and the type of displacement is going to be different in that the hanging wall is going to move down relative to the footwall. Now, we always have to talk about these things in the aftermath. We don't know really which block moved, was it the hanging wall or the footwall. All we know is that this displacement has offset some material. So we talk about one block moving relative to the other block. In the case of normal faulting, the hanging wall moves down relative to the footwall. These are going to accommodate tensional stress. So again, tension is pulling. If you're pulling on some block of material, particularly again if the angle's low, then the result is going to be that the top block is going to move down relative to the bottom block. This accommodates extension, it accommodates lengthening, whereas reverse faulting accommodates shortening. It makes the crust thicker, but it doesn't take up that much room on the surface of the earth because it's shorter but thicker. Block faulting is just one particular sort of variety or sort of special case where you have normal faulting. And these Horst and Graben structures are really beautiful in real life. So I kind of wanted to show you what these things end up looking like. In this case, you end up having these banded normal faults. So all of the faults that are going to allow for the displacement of all of this material, they're all going to be normal faults. But they're going to be moving in different directions. They're going to have, maybe the better way of describing this would be that all of these faults are going to be at different angles. So the Graben part of the structure is going to be the central part of the middle picture here, where you have the down-thrown block. It's surrounded by 2 normal faults on either side, and those normal faults are allowing the blocks on the right and the left to be moved up. The Graben structure is going to be moved down. On the very lowest diagram, the one marked D, Horst, the Horst structure is going to be this up-thrown block in the center, whereas the other 2 blocks are down-thrown blocks. But if you really look image by image and look at all of the faults involved, they're all normal faults. They all have the hanging wall block, whether it's on the right or the left-hand side of that fault. It's always above the plane of the fault. The hanging wall block is always moving down relative to the footwall block. The thing about Horst and Graben structures and block faulting is that these faults are usually going to be fairly high angle, 70, 80 degree angle, and they're going to accommodate most of the actual vertical uplift that associates with mountain building. So you've got all of these individual faults, all normal faults, that are all allowing for the overall mountains to be uplifted. That what's going to allow this to happen is that some is going to be uplifted more. Those are the Horst structures. Those are going to be the uplifted blocks. The Graben structures are going to be dropped down a little bit relative to the Horst structures. But then all of this is moving upwards altogether. So our overall last type of fault is going to be called a strike-slip fault. So the other two, those were both dip-slip faults. If you're thinking about the fault as a planar feature, the motion where you have a fault that has motion along the plane of the fault and one block is moving down or up relative to the other block, those are always going to be dip-slip faults. To understand a strike-slip fault, it's easier to view these from above or to view these on the surface. Because what's actually happening here is that the motion is along the strike of the fault, the orientation of the fault at the surface, and not up-down. So you don't really have mountains and valleys and things like that in strike-slip faults. You mainly have the offset of features that were perfectly straight on the surface of the earth. Like let's say if you had a fence line, that fence line would no longer be straight. It would end up being crooked over time because of the motion along this fault. So in strike-slip faults, you have one block, whether it's to the right or the left of the fault, it doesn't really matter. One block is going to move an offset. It's going to slide past the other type of fault. So the sliding probably makes you think of the type of stress that's going to be accommodated by this fault. It's a shear stress. So the fault itself is right along strike. That means it's usually going to have a very high angle, like vertical or nearly vertical. And then the blocks of material are going to move in opposite directions. So let's say one hand of mine is at one block, the other hand of mine is the other block. They're going to move in opposite directions to the fault itself, exerting a shear stress. So these types of faults are really bad about triggering earthquakes because you have a lot of brittle deformation. You have a lot of stress that's building up fairly close to the Earth's surface. So the release of earthquakes, which is going to be the topic of our next video, is going to be more common and typically a lot more catastrophic when you're dealing with strike-slip faults and when you're dealing with faults that occur closer to the Earth's surface. So that's our three different types of faults, all part of our geologic structures lecture. And to end the lecture today, I wanted to take you guys on another field trip. Something definitely to get used to because we're probably going to be doing this for most of the lecture videos. In this case, I'm going to take you on a little field trip that's going to show you what's going on with one of these different types of faults. So I hope you enjoy it. All right, so our last field trip took us to the Grand Canyon, and on this one we're going to go about 100 miles southwest of Grand Canyon to an outcrop near the city of Kingman, Arizona. Now, this outcrop is actually in the form of something called a road cut. So what you're looking at right now is a road cut. It's something that needs a little bit of an explanation here, whereas I might not need to explain it in some place like Arizona or Colorado, because of course we don't have any mountains to cut through to build our roads here in Louisiana. So in mountainous places, you have to occasionally blast out large sections of rock in order to be able to put an interstate or to be able to put a highway through a mountainous area. And that's the case here in Kingman, Arizona. So this particular road cut was blasted on the north side of Interstate 40, just outside the city. And what it exposes for us are these wonderful normal faults. Now, it's not just this particular road cut. Geologists love road cuts in general because it gives us this cross-section into the earth that we wouldn't originally have. It gives us this ability to actually see what a slice of the Earth's interior looks like, and it gives us this fresh, unweathered surface. So in this case, it gives us this view of these banded normal faults. And in a normal fault, the hanging wall drops down relative to the footwall. So as you look at each of these individual faults, you can see that that's indeed what's happening. And it's the variation in the colors of all of these different layers that allow you to see the offset really nicely in this location. So these normal faults are doing what all normal faults do. They accommodate extension, and in this particular case, they're accommodating uplift. And this uplift is the uplift of the entire Colorado Plateau. It's the whole reason why the Grand Canyon exists where it does too. This entire area, Arizona, parts of Colorado, parts of Utah, were uplifted millions of years ago with the rest of the Rocky Mountains. And that's part of the reason why these faults are now exposed for us here. So I hope you enjoyed that. Until next time, keep rocking.